kind of talks about like pseudo M order, and we kind of like show that we have to like increase M really big, or then increase the concentration, and
okay,
really,
what
like,
was it?
Yeah, it's right here.
Number 15. Where does M and N originate from?
Yeah.
Okay. Yeah, in the rate law, K A to the M, B to the N for the reaction A plus 3B yields G. Where does M and N originate from? Does anybody have the answer for that? Yeah, where do M and M come from? The mechanism. And so the answer to that is the mechanism. Or you could be more specific. It's the slowest step of the RDS in the mechanism. Or just the mechanism. Really fine. Oh no, that was free response. Okay, other questions?
Yeah, number 14. In the reaction, A plus B goes to G, goes to H. G is a
Intermediate.
G is an intermediate, that's correct. B.
Okay.
Might as well keep it. What? I guess we need help on
All right.
17 too.
Okay. What was next? 17? A yields product. What is K? What is rate law? What is A when T equals? Yes. And so how would you do number 17? What approach did you take?
Like 16 is a better question.
Well, you can do 16 too.
Is 16 going to be covered on the test?
Yeah.
Yes. Is this the activation energy, like the plots of like temperature and
Well, what's a Maxwell-Boltzmann?
doesn't it just map out the
Population versus energy. It looks like this.
yeah.
This is from chapter 6. Show how K changes with T. Maxwell-Boltzmann distribution. So where we get the Arrhenius equation from. K is equal to A e to the minus e sub a over RT. This is not the Boltzmann constant. This is the rate constant.
Boltzmann constant.
Rate constant. And so in this particular plot, where does the temperature show up?
Well, if you increase the temperature, it'll shift the energy, like the graph is right.
Okay, and where does the activation energy show up?
I know it's to the right.
Yeah, it's somewhere here. You know, activation energy changes depending on energy transition. If the bonds are easier to break, the activation energy goes down.
Yeah.
Bonds are harder to break, the activation energy goes up. But let's say, you know, it's just a fixed reaction. Well, how can we speed up that reaction? One thing you could do is shift the distribution by increasing the temperature. Right? And so if we increase the temperature, then the population shifts to the right, like that. And so now the population grows. So this is this. That shows it. And so as we increase the temperature, we expect a larger population. A larger population would mean a faster reaction.
And EA is specific on the type of, like what's reacting and the temperature? Is that where EA is drawn at? Or is it
EA comes from the transition state. This diagram. EA comes from, if I had AA reacting with BB, the transition state is going to be this complicated structure where the bonds are breaking and forming at the same time. So EA is related to the bond energies here. The harder the bonds are to break, the higher the activation energy should be. Okay. But it's not directly related to bond energy. It's not equal to the bond energy because bonds are forming at the same time. So the question is, show how K changes with T. Well, if we increase T, we'll increase the population here, which increases K. Rate constant. So the reaction should go faster, higher temperatures.
So that'd be an okay answer, just raising temperature and raising population and raising K?
Yeah, because this is a T, this is a, a temperature greater, increase in T. In the second curve.
Wait, is an increase in population the first way of describing it? An increase in population. So is that an accurate way to describe?
Now, how else would you describe it? Using this curve?
Technically, it looks like the population went down.
Where? The population, the total population is the same.
Right. Yeah. It also sounds like you're adding more concentration.
Population went up. It was originally here, now it's here.
So the population of what's reacting.
Yeah, nothing below EA is reacting.
Yeah.
The only thing that's reacting is it has to have this minimum energy. And so the population is the whole thing now. At lower temperature, this is the population. A higher temperature, now this is the population, the whole thing. Population. In other words, it's the area. Did the area under the curve grow above EA? If the area grew, then the population grew.
Sorry, it just sounded like concentration was going up.
No, population. Other ways you can increase K. There are two ways you can increase K using this. One, increase the temperature, or two, decrease the, what's the most common way of decreasing the activation energy for a reaction? Enzymes or catalysts, right? So with a catalyst, you can also increase the population because if EA shifts this way, what's going to happen to the area? It's going to go up, no matter what the temperature is. It's going to go up. Okay, that leaves number 17. Number 17, which approach would you take to solve that? Were you guys on number 17 stumped on this or not stumped? No. No, it wouldn't unless you know something about it. Just because it says A goes to product, you can't assume it's unimolecular. A goes to product, it might not happen in one step, It might happen in 2 steps, or it might happen in 3 steps. How many steps does it take to go from A to product, even though it's only one molecule? So it's tricky because you don't know what the RDS is or anything else. You would assume it, yeah, maybe it is, unimolecular. But, what if I wrote something like this? 2A goes to product. You'd think that's bimolecular, right? But you don't know because let me do this. Calcium carbonate goes to product, calcium oxide solid plus CO2 gas. What is that? Unimolecular? And then if I do this, 2 calcium carbonate, 2 calcium oxide plus 2 CO2s. Bimolecular? What if I'm going to go infinity calcium carbonate, infinity calcium oxide plus infinity CO2. Infinity molecular? No, because is this wrong? Outright wrong? Can I take 1 mole or 2 moles, or does it make a difference? This is not wrong, right? Is this wrong? Maybe, but this wouldn't be, or 3. And so just because you wrote a coefficient there doesn't mean that's the order. The only way you know that's the order is by... How would you know that's the order? How would this...
The mechanism and the steps must equal the overall.
No, I think I gave you some questions on the multiple choice, didn't I? You could say it's unimolecular if what were true. Yes. You could say it's bimolecular if what was true. This would be bimolecular. That is, the rate is equal to Ka squared if what were true. If what?
If it's a simple
Yes, if it's a simple collision or a it's another
elementary?
word for elementary step, right? If that were an elementary step, well, how could you know if it's an elementary step? No, not if it's fast reversal. What question is this for? Is there a question in there, or just a general question? Just a general question? Okay, how would you know? Okay, if it's elementary.
No intermediate.
Yeah, there are no intermediates. It's just one step, one single step, right? That's it. And then it's called a elementary step. And the rate law is easy. But how do you distinguish, you know? Is this one elementary or is this one elementary step? And so I did a long discussion about this reaction. Is this a trimolecular or termolecular collision?
It looks like it, yeah.
So if it's a termolecular collision, then the rate is simple. The rate is equal to, we need methane to collide with 2 oxygen. Right?
Mm-hmm.
There's intermediate steps.
But there's intermediate steps. And so it's not termolecular. It might, I mean, the rate law, the problem is there are hidden steps in here. If there are hidden steps, each of those individual steps are what we call, well, the whole thing's a mechanism. Each of those little steps is called a elementary step, right? And so how do we know if there's hidden steps in here or there are no hidden steps in here? How many hidden steps are there in the combustion of methane? Hmm? Too many? About what? 5? 10?
I'm going with 1,000.
Hmm?
1,000.
Yes. Okay. Did you know that? I mean, could you have guessed that?
You said it, yeah.
I told you guys, right? But how could you have known? You couldn't have, right? And so somebody has to tell you if it's elementary or not. And if they don't tell you it's elementary or not, then what are you going to assume? That it's elementary? If nobody told me there are 2,000 steps here, then I'm going to assume there's only one step. It's just elementary process. It's termomolecular collision. Simple. 3-molecule collision. Would you assume that? No. You wouldn't. Why would you assume something like that? Who knows? Right? And so if somebody told you this were a simple collision or elementary step, then yes, it's unimolecular. It would be first order in A. Right? If somebody told you this was a simple elementary step, then yeah, it's bimolecular. But if nobody told you, then why would you assume that? You can't. Because there could be a whole bunch of hidden steps. And the slowest of those steps might not be two A's colliding with each other. Does that answer your question about that? And so the only way what you said would be true is if it were elementary step. The only way you'd know if it was an elementary step is if somebody told you. That's why I asked you, what was the question? If somebody said it's an elementary step, then yeah, it's easy. If somebody didn't say, then it's easy still because you don't know.
It says 2A to 5, and then the rate equals A, the concentration of A to N. Would it be not enough info? You can't assume.
What is the question asking for?
It's just saying what is N.
What is M? Isn't M equal to 2? Well, if it doesn't tell us, can't I assume that there are no hidden steps in here? Just like, if they didn't show 2,000 little arrows here, then it just must be one arrow. Right? So what do you think the answer is? Not enough info. Right. It's impossible. How can you tell? Just like I asked you, I'm going to ask you to tell me how many steps there are in this methane combustion. Oh, you're supposed to know that. There are over 2,000 steps. Is that a fair question? No, not enough info, right? If I asked you how many steps there are in this decomposition, 2A goes to product, you don't even know what A is. Right? A is just some generic compound. Who knows what that is? Are you going to assume every generic compound called A is going to react like that? No. Not enough info. Right? On the other hand, if somebody told you we're elementary step, then there's enough info. Elementary steps are simple because there's nothing hidden. So that was the point of this methane stuff. And then subsequent talks. You know, I did the Tesla. You left this drive, computer lab. Somebody left that. So, you know, this A plus B. You know, the rate is equal to K A to the M, B to the N, or equal to K A to the little a, B to the little b. I wrote both these equations. Yeah. And so what's the difference between those two equations? Yeah, which ones were elementary? And which ones were non-elementary? The top, and so that's it. How do you know it's elementary? Is this an elementary one-step reaction? No. Well, it might be, but how can you safely assume it is? And therefore, the only safe thing to say is you don't know. Well, anyway, that was a major point you should get.
Yeah, I'm still kind of confused on that one. Because it gives us concentrations in time and asks what K is in the rate law and what concentration is at.
Well, you did this in lab, right? In lab, you did this. You took the time, remember this? And the concentration of crystal violet. But you had a lot more than 3 data points. So how did you figure out what to do with that? It's time versus concentration.
And then you do ln of CV for time and then over
Yeah.
CV.
Yeah, we made ln of CV over, and then 1 over CV. Remember that? And then we made 3 graphs.
Straight line.
The one with a straight line,
That's the order.
that's the order.
This is the one where we're finding a bunch of K values.
And so the problem with the test is graph. Maybe I should give you graph paper and you can figure it out. But graphing takes a lot of time, so normally I don't give you graph paper. Normally I don't give you a huge data table, otherwise that would take even more time. And so as an alternative to graphing, what did we do? Well, we calculated the
Percent change, the percent difference,
the percent difference of what? The K's, which are the slopes. And so all we did was, but you know, we could have done it just graphically. I showed it graphically, you know, concentration versus time, and we only have 3 data points, and so we look at this segment and look at what the slope is here, and then we compare it to this segment and look at what the slope is here. Do the 2 slopes agree? You know, this would be the slope of 1, but you know, slope is also called K, so actually minus K is the slope. So K is equal to the negative of the slope. The slope is going to be negative here, so it'll turn out to be a positive. So we calculated the slope for segment 1, and then we calculated the slope for segment 2, and then we saw the percent difference. Hopefully the percent difference is 0. If the percent difference is 0, it tells you it's
good.
Straight line, linear, right? If the percent difference is not 0, like say you calculate the slope for segment 1, it's like this, and then all of a sudden the slope for segment 2 is like this. Does that look like a straight line to you? No, that's got to be a curve. And so when we compare the 2 slopes, K1 and K2, the percent difference is going to be big. And so what we're looking for is the smallest percent difference between the K's. But you know, you guys know how to calculate the slope. And so we could calculate the slope here. And it's fine. You could do it like this. Y2 minus Y1 divided by x2 minus x1. Okay? In this case, y is the concentration. Y2 minus y1 divided by x2 minus x1. In this case, y is the natural log. And then you could do one more plot. 1 over the concentration. Y2 minus Y1 over X2 minus X1, which would be X. In this case, Y would be the inverse of the concentration. And then you calculate the two slopes. See how well they agree. You could do that, but there's a quicker way to do that. And the quicker way to do that is, I did this exact same problem with different numbers. Did you guys look at that one? What was the problem we did in class? It was hydrogen peroxide, right? Hydrogen peroxide, I talked about the slopes, and then I said, well, this takes too long. There's a quicker way of doing it, and the quicker way of doing it is just by doing K analysis. I call it K analysis because it's not really calculating the slopes, it's calculating the Ks. Now, if you have your notes, can you just take a look at your notes and then look, did I do a Y2 minus Y1 over X2 minus X1 anywhere? No. Instead, what I did was K for segment 1, K for segment 2, and use the integrated rate law. Because the reason I use the integrated rate law is it's a heck of a lot faster than calculating the slopes, Y2 minus Y1. But it doesn't matter. Whatever way is more comfortable to you, do it, because both will give you the same exact answer. And so rather than doing this here, and I can spell this out for you, but basically I just mentioned it. But it's, final concentration minus initial concentration, final time minus initial time. That's the slope. And then we take the negative of the slope because K is the negative of the slope. But I said, don't do this. It takes too much time. Do this instead. K for segment 1 is going to equal ln of A, right, at time t over A initial, that is final over initial, divided by the time. And this is the time segment, so whatever that is. This is actually a delta t, how long that time is. And this saves you a lot of button pushing and a lot of writing. And so we see what the time segment here is just the time interval. The time interval between. Do you see that in the hydrogen peroxide problem we saw? Mm-hmm. So this problem is exactly the same. You could do it either way. I did it both ways for the hydrogen peroxide, at least showing it both ways, but I didn't actually do the slope calculation. That takes too much time, so.
In order to do that way, we need to know the order of the overall first, right?
No, because in number 17 it's like this. Number 17 is time versus concentration. Give me the time. 0,
1 minute, and 5 minutes.
and the concentration.
1 molar, 0.89, and 0.61.
Sometimes you could just look at it by sight and see. In this case, can you easily? No. A little bit more complicated. So I just look at the slope. The slope between the first 2 points I'll call K1. The slope between the second 2 points I'll call K2. I don't know. But we'll soon find out because this is...
My question was regarding the integrated rate law, because there's G over the first order and second order.
Oh, okay. Do you have to have those memorized? No, I'm going to give you the integrated rate laws, but you'll have to know which ones go for which.
Okay.
Did you already memorize them?
Yes.
Oh, really? You're gonna fly to it?
Well, that's good to have them memorized, because people who don't memorize them ask me, is this the right equation to use
During the test?
during the test? Yeah.
So you just.
No, I'm not going to tell you. No. So K, what is K? If it's zero order, then K is what?
Constant.
Yeah, but it's equal to what? From the integrated rate law, A times T minus A initial over the time segment.
Yes.
Negative. So the time segment here is
It's 1.
1. The time segment here is 4. So this is just like calculating delta y over delta x. If it's straight line, then the percent difference between those two should be close to 0. Then first order,
The natural law.
yeah. This is actually the slopes, but it doesn't look like the slope. It doesn't look like we're calculating the slope, but we are calculating the slope. This is the slope. And then for second order, K is equal to 1 over final minus over the time segment. This doesn't have to be multiplied by negative. So all we're doing is calculating two slopes here, and two slopes here. Which of those two slopes
Closer to 0.
are the same, or close to being the same? The one with the smallest percent difference. How do you calculate the percent difference?
The two slopes that
Small
are
minus large.
The biggest minus smallest divided by
smallest.
smallest times 100%. And then see which one gives you the, 0% means it's linear, straight line. And so this is just saying, what graph is linear? Concentration versus time, L on a concentration versus time, or 1 over A versus time? Which graph is linear? That's all. But it's asking you but with only 3 points of data. With 3 points of data, is that safe, or is that a little bit
It's not very good.
not as good as having a lot of data?
Yeah.
Because everything looks everything starts out looking pretty linear at the beginning. But you don't know. Is it going to continue looking like that, or is it actually going to curve away? And so if you only have 3 points tightly spaced at the beginning, that's not so good. It'd be better to have, maybe you could have 2 points tightly spaced, and then the third point might be either here or here. Like spread out. And so this is why, do you see these two are pretty tight, but this one's a little bit farther out. Let me see. All right, that's only to figure out what
Order.
what order it is. Once we figure out what order it is, the rate law, there's only one reactant, so it's going to be Ka to the M. And so M we determine from this. What did I do for the reaction? What was it? 2A, 3A?
Just A.
Just A? Well, isn't it, if I just have A, isn't that automatically first order?
No.
No. All right, now once I know what the order is, then what do I do to answer the second part?
What is the rate?
What is K and what is the rate law? Well, K is going to be whatever K is most constant. You just take K1 plus K2 to get K average. So we'll get our K average. You know, there could be, the reason why we do the average is because there could be slight experimental fluctuations. So it's better just to take the average of the two slopes rather than just one of the slopes to minimize random error. And then to calculate the second part, it says how long or how much, or what does it say?
What's the concentration of A when T is equal to 60 minutes?
Okay, well, when we have a T equals 60 minutes, then we'll need the integrated rate law. And so one of these we'll have to plug in T here, the initial concentration, and K average, and solve for the other, the missing. And so we use the integrated rate law to figure out the concentration at any time T. But in order to figure out which integrated rate law we use, we needed to know the order first.
What if the percent differences are all off?
Then there's probably some kind of error. You know, either if you have 3 points really tightly spaced, then they could be close to each other. You just do the best you can do. You would pick the smallest one. You might look if there's a calculation error, because, you know, really only one should be linear.
When we're trying to find the concentration of A at T equals 60 minutes, could we do something like use which initial should we use? Can we use like at 5 minutes, or does it matter? Do we have to use 0 at 0 minutes?
Doesn't matter.
Like, could we go like the 5 minutes? So then, if we use like the 5 minute one, we could go like 55 minutes instead. T equals 55. Right?
Yeah, except the initial, you'd have to use
And then yeah.
0.61
So we can
instead
still do
of
that.
1.
Would
Yeah.
it give us the same answer?
It'll give you the exact same answer. Yeah.
What was the acceptable percent error?
What would be an acceptable percent error? When,
0.
not percent error. It's not percent error. It's percent difference. 0. 0% would be good. The closer to 0 you can get, the better. It depends on how good the data is, because for for made-up data, and the data is perfect, then close to 0 you're looking for. For just experimental data, well, you don't know who's collecting it, or what they're doing with it, what the precision of the instrument is, and so it could vary quite dramatically. But we don't worry, because we're stuck. Whatever our percent errors are, that's what we got, assuming we did the calculation correctly. And so all you have to worry about is finding the lowest. Now, I went into a long spiel about this. If one gave you a 10% versus 12%, is it clearly one over the other?
No.
No. In this case, you'd start to have second thoughts, because both of these are kind of bad data. It's hard to predict. Let's say you're analyzing your unknown acid. And so unknown acid 1 gave you 189% error. Unknown acid number 2, your second choice, gave you 191% error. And you go, oh, yeah, that's my acid. That's my acid, because that gave me the smallest percent error between the molar masses, the experimental molar mass and the molar mass given in the table. What would you think?
No.
I think not, yeah. you would start to worry. Is that enough to finish this problem, or?
It also asks, how would you change this experiment to make the calculations more accurate?
Okay, how could you change this experiment to make the calculation more accurate? More data. More data. This is only 3 data points. You know, random fluctuations are going to be more significant. It's like this. You know, if you had a 1-drop error, is that big?
Depends on the concentration.
It depends. A 1-drop error in filling your swimming pool, if somebody asks to fill the swimming pool to this volume, oh shoot, I overshot it by 1 drop. Are you going to drain it and then start over again? No, but let's say a 1-drop error in your dosage of, let's say some toxic chemotherapy agent. You know, 1-drop error could be significant, and so to minimize those, you know, the relative, that's what we call relative error. To minimize that relative error, you know, the more data we have here, the less significant each little random fluctuation will be. Okay, was that it for that question? So more data. The more data, the better, because when you're doing a trend line fit to a linear line, you're not just averaging 2 points, you're averaging all your points. And so if you have 60 data points, that's an average of 60 data points, which is going to be much better than an average of 3. Right? In Chem 1A, I see this all the time. Sometimes it helps people, you know. In Chem 1A, there's an experiment. I forgot which one it was, but they take 3 averages. And so let's say in average one, percent sulfate. Did you guys do that lab? The percent sulfate lab.
Yeah.
Qualitative analysis. All right, trial 1, 40%. Trial 2, 50%. Trial 3, 60%. Okay. And the average would be 50%. And so then another person comes along. Trial 1, 50.1%. Trial 2, 50%. Trial 3, 49.9%. Well, I don't know if this is going to illustrate my point very well, but these both give the same average, right? But
The differences are greater from somebody else's data versus.
yeah, which student do you think did a better job?
The second one.
Yeah, and which one would you trust?
The second
How could you trust this? If this were all the data you got, how could you trust this? You can't. You'd want to collect more data until you could clearly see, because the more data you collect, what happens is you start building up this thing that is called the normal distribution. And so if you could take an infinite number of data points, some data is going to be high, some data is going to be low, but eventually you're going to get the true average, because even if you screw it up like this, you know, the probability is you're going to screw it up both ways, but eventually your technique might improve by the time you're doing 1,000th measurement, and so you'll get this and get the true average, right? And so the more data you have, the more likely it is you're going to get the true value. Okay, other questions? From the practice test or homework or whatever?
Go over number 69 on the homework.
Number 69 on the homework.
It's 2NO.
2NO.
Plus CO2.
Okay. NO plus Cl2 yields 2 NaCl.
Probably tells you that's like a two-step.
Two-step mechanism.
Yeah, and the second one's your
And so step 1, step 2 is the RDS. Right?
Yeah.
This is fast reversible.
Yeah.
So we need to come up with a two-step mechanism. But this two-step mechanism has to agree with this. And the rate law for this is, what order in NO?
2.
And what order in CL2?
1.
Oh. This has got to be a one-step, right? This has got to be a one-stepper because it's 2 and 1. This has got to be a single termolecular reaction. I mean, a single step termolecular reaction. Yes?
No.
Absolutely no? Or probably no? Absolutely no or probably not? Probably, it could be. This could be a single step. Because a single step would yield this as the rate law. And so what we could say is that a single step mechanism is possible. In other words, a single step mechanism is consistent with the rate law. But maybe we could get a two-step mechanism that could be consistent also. And so let's see if there's a two-step mechanism that is consistent as well and see which one you think would be better. And so for the first step, we have different choices. We could do maybe a unimolecular collision. Yeah, okay, Cl2 collides with the wall to break up into 2 Cls. Boom, there's a violent collision. Because Cl2 at room temperature, are all Cl2 molecules moving at the same speed? No. What kind of distribution of speeds do you see for Cl2 at room temperature? Chapter 6, what was the speed? What did the speed distribution for a gas look like?
The more speed, the quicker the particle.
No, I mean, what did the population distribution? If I have a mole of Cl2 at room temperature, is every single Cl2 molecule moving at the exact same speed? It's kind of like a bell curve. But we don't call it a normal distribution or Gaussian. We call it a... What does that curve look like?
Skewed to the right.
The population curve or a... This is a energy. Thermal population. It starts with an M. This is called a Maxwell-Boltzmann distribution. In the Maxwell-Boltzmann distribution, a tiny fraction of chlorines will have a very high energy. High enough energy so that when they strike the wall, you might break the bonds. But the bulk of them, maybe they don't have enough energy to break the bond. The bond energy would be the cutoff here. What's the bond energy for a chlorine-chlorine bond? Activation. All right, this would be step one. It's fast reversible. Fast, I don't know how fast. Depends on what the population there is. But the next step would be Cl plus
Cl plus 2NO, or wait, 2Cl plus 2NO.
2Cl plus 2NO yields 2NoCl.
Wait, quick question. You said there were multiple choices for the first fast reversible?
Yes.
Isn't that false? Because can NO break up like to radical nitrogen and oxygen?
Possible. Because NO also has a population distribution in which it depends if it can exceed this energy here, could break the bond.
Yeah, I thought you said one time that nitrogen doesn't like exist anyway, so.
It doesn't, but it can. It can, but it doesn't last long. Free radicals, do you think free radicals are stable? Free radicals are things with dangling bonds. You know? They aren't stable. They want to attack something right away to become stable by forming a bond. The nitrogen is the same way, but that doesn't mean it can't form. Because what do you think is in the flame? In a flame, there are free radicals in the flame. Did you know that? There are. And there are ions in the flame. There are a whole bunch of species, but you say, well, aren't those unstable? Yes, they're unstable. Do they last very long? No, they don't, because by the time you inhale the fumes from the flame, most of those are already gone, right?
So in mechanisms, can we have nitrogen as a...
Yeah, we can.
Oh, okay.
We can try it. But what's wrong? What would you think about this mechanism here? Does this look very good to you?
No.
Why not?
It's like CO2 more stable than CO.
Yeah, that's true. But that's not the killer. One of the killers for this is this second step. What is the second step?
It's like, yeah.
Tetramolecular from four molecule collision. Is that very likely? No. So this is starting to not look so great. So let's go to NO. Maybe NO collides with the wall to form N and O. And then N and O, and then two NOs. Oh no, that's not it. Does this work?
No.
I know. It's got to be NO goes to N minus 3 plus O
No.
minus 2.
No.
Nitride and oxide. What's wrong with this? It's not that. I can make it balance. N2 plus plus O2 minus. That's it?
No.
No. That's not it. So let's give up on those. Let's move on to something else. Maybe it's not unimolecular. Maybe it's a bimolecular. So one thing you could do is collide two NOs. There's no problem with that.
That's the first step.
That's the first step. What would this form? It could form N2O2, and then the N2O2 can collide with to form 2 NoCl. Does this look reasonable? I think it looks reasonable because N2O2 actually exists. It's a compound.
But that mechanism, though, like would the orientation be like really weird?
For which one?
The collision, the second step.
The second step? Why?
I don't know. They're like, you're telling me like when they collide, it's gonna like magically just turn into NOC. Magic.
Depends on the Lewis structure for N2O2. What is the Lewis structure for N2O2? We got to figure out the Lewis structure. Is it a ring like this? Probably not.
No.
Four membered rings, the most stable.
I would think that nitrogen, yeah.
Is it something like this?
That's what I would guess first.
I guess it,
Then the Cl comes like this, and nitrogen comes like this.
alright, so I guess the orientation's not
Hmm?
okay, no, never mind.
I don't think it's a big issue.
Yeah, I don't think so either.
Yeah. I think we can figure it out. So anyway, the rate, the second step's the RDS. So the rate is equal to K2 N2O2 Cl2. N2O2 is the intermediate, so we're going to use the fast reversible. Fast reversible says K1 NO squared is equal to K minus 1 N2O2, right? And then solve for this and substitute it in here. So do that, we're going to get NO squared. So this is going to come out K prime NO squared Cl2. So we get the same rate law, but with a bimolecular collision instead of a tri or termolecular collision, right? Which is better, do you think, or more probable? The bi. And so this this mechanism probably is more likely than a single collision. So this is step one, step two. But you can't rule this out, right? Maybe some forms this way. Because both of these are consistent with experimental data. But does that mean there aren't other mechanisms that might be consistent? For example, what if we did this? There's step one. NO plus NO goes to N2 plus O2. N2 and O2, that's nitrogen and oxygen. Seems pretty stable, right? But then we look at step two and we go N2 plus O2 plus Cl2. Now, that's starting to look less probable. You know, if you had nitrogen, oxygen, and chlorine in the air, you know, air is already nitrogen and oxygen, a little bit of chlorine in there, it might make a little bit of this, but well, maybe this is it. But again, this is a try. So you can try other ones. NO plus NO yields N2O plus O, etc. But we didn't try this. We could have tried NO plus Cl2. NO plus Cl2 yields NOCl plus Cl. How does this one look for the first step? Yeah, not bad. And then step two, Cl plus NO yields NOCl. This one works. This works. We just got to make sure the rate law matches. And so the rate here is equal to K2 Cl NO. Cl is an intermediate, so we'll use the fast reversible here. That is K1 to 4 is NO times Cl2 is equal to the reverse, K minus 1, which is NOCl times Cl. And then solve for the intermediate, Cl, and substitute. So we end up with K prime, and substitute this. This is going to be NO, but NO times NO is NO squared. Looking good so far. And then this Cl2, that's good. Everything looks good so far, except for NOCl. It's got to be divided by NOCl. Does this look consistent with that mechanism?
No.
No. And so we'll rule these out. All right. So that's number 69. Uh-huh.
In our homework, we have something that it had like the D of the concentration of the product over the DT. We don't need to know that, do we?
No.
Okay.
Well, what's that D representing? What?
The rate, we had this, you had to know. The rate is equal to the delta, the change in concentration over the change in time, the slope. But this is what we call the average slope. But we also have this. We have d concentration over dt. This is what we call the instantaneous. It's instantaneous because what d is delta, you know, at its limit. That is, when delta becomes very, very, very small, then the slope is going to look less like an average and more like an instantaneous slope. And so when we're looking at a curve like this, and we look at the slope between these 2 points, does that look like the instantaneous rate or the average rate between these 2 points? That's the average. But as the delta becomes smaller, it starts looking more and more instantaneous. Pretty soon the delta is so small that it's focused right here, and then that slope looks like the instantaneous slope rather than the average. We don't have to worry about it. Okay, what else? You guys have questions? That's it? All right. Well, if that's it, then we have to move on to thermo. Where did we leave off in thermo? Thermo and kinetics are 2 different things, right? Thermo, we deal a lot with state functions. State functions is just, you know, your final state, initial state, or initial state, final state. You know, it goes up or goes down between states. Delta H, delta E, delta U. Kinetics, we look at the path, right, between those 2 states. So we spread it out like this, and we look at some kind of path. Is that a elementary process or not?
I would say not.
Is this a product? Yeah. Is this a multi-step or a single step? Let me give you something to compare with. Versus something like this.
Okay.
The blue one would be like a 2-step. Right? Black one should just be a single step.
Just kind of reviewing chapter 14 stuff. So that would mean that there would be 2 transition states, and there
Yes.
would be 1 intermediate with the
Yes.
blue one. Okay.
Right. This is the intermediate here product. 2 activation energies, 1 here and 1 here. Which activation energy is bigger?
Second part.
The second one will take longer.
The second one. The second one is a bigger hump to climb than the first one. So the second step would be the slowest step. Sometimes we have something like this. Which one is the slow step here?
First one.
The first one. The first one is going to have the higher activation energy. The second one's activation energy is actually quite small, so it would be very fast. So the analogy everybody uses is if you're riding a bicycle, you know, where's everybody going to clump up? You have a whole distribution of riders. And so probably at the bottom of this big hill here, everybody clumps up, but going over the second hill there is no problem for most people. Just cruise right over it. And so the RDS would be the first step. Well, typically, in thermo, you know, a highly exothermic reaction is usually very fast, but it doesn't have to be because kinetics and thermodynamics looks at two different things. Right? Kinetics looks at the path. One way we can lower the path, speed up the reaction using catalysts, but that's not going to change delta H. You know, if I add a catalyst in there, does that change delta H or any other thermodynamics? No, because all we care about is the reactants and the products. So in the catalyst here, you got a catalyst there, the catalyst cancel. So we were looking at driving force. Where did we stop? We were looking at the driving force for reaction. Delta G of the system. Did we talk about the second law of thermodynamics?
Yes.
We stopped at like talking about work.
Work?
Yeah.
Okay. All right.
We spent a lot of time on appendix D.
Okay. Did we derive this equation? Delta G is equal to delta H minus T delta F? I should have written in delta G of the system is equal to delta H of the system minus T delta S of the system. We did that? Okay. And so this tells us the entropy of the universe, basically. Because delta G of the system is defined as minus T delta S of the universe. And so delta G is a new state function. It's called the Gibbs free energy. And if delta S of the universe is increasing, then delta G is decreasing. So if delta G is less than 0, then it's spontaneous. If it's equal to 0, then we say it's kind of at equilibrium. There's no change. If it's greater than 0, then it's non-spontaneous. But in the reverse direction, it would be spontaneous. Okay, so in other words, if delta G is less than 0, the entropy of the universe is increasing. So if delta G is less than 0, the entropy of the universe is increasing. So here, like delta S of the system, it's easy to see. You know, the more negative this term is, because delta S of the system is positive, that means entropy is increasing, which makes this term negative, more negative here. Temperature is always positive. And if delta H is exothermic, you know, then the entropy of the universe must be increasing. Now, if delta H is exothermic, how is the entropy of the universe increasing? Well, that has to do with energy. Did I talk about the energy content of the universe?
You said the heat has a higher energy than chemical potential energy, which can be converted to work.
The heat has a higher entropy.
Oh.
Entropy. Yeah, so when we look at the exothermic reaction, how is being exothermic increasing the entropy of the universe? Well, one way to think about this is energy entropy. Energy entropy. And so if we start off with methane plus 2O2 gas, this produces CO2 gas plus 2 H2O liquids. There's going to be a delta H for this. And the delta H is less than 0, so it's exothermic. And so what we're doing here is this. If I look at the internal energy, actually it'd be easier to do internal energy. It doesn't matter. What's changing here? Well, if this is at 298 Kelvin, and this is at 298 Kelvin, so we start the reaction at room temperature, we end it at room temperature. So we just burn some methane, it gets hot, and then we let it cool down back to room temperature. A lot of energy was released to the surroundings, right, by burning the methane. And so that's what we see here, energy being released in the sun. Well, where did that energy originate from? Yeah, it originated from the bonds. And the bonds are what we call chemical potential energy. There's two ways to heat up this room. One way is you can transfer the heat from a hotter object into the room, right? And so we just bring a large hot object into this room and let the heat dissipate off that. And so that's just a transfer of kinetic energy. The hot object has high kinetic energy. The room's a little colder, has lower kinetic energy. And those collisions are going to cause the transfer of energy, right? Of the heat. Or you grab a hot object, you know, you grab the hot metal, you're transferring the kinetic energy from the metal to your fingers. And so that's just heat being exchanged for heat or kinetic energy transfer. But this is a little different because is this a hot object? Is this a hot object? No, so all that heat's being generated from what? All that heat's being generated from the bonds. The bonds we call chemical potential energy. And so this is an unstable, high energy mixture, methane and oxygen. This is a stable, low energy mixture. And so this is what we call chemical potential energy. And so what we're doing is we're converting the chemical potential energy into heat. You know, the kinetic energy that's forming up whatever. And so the energy entropy is this, you know. What do you think is more usable? Say you want to build a car. You know, putting a hot chunk of iron under the hood and making it go, or burning methane and oxygen under the hood to make it go. Yeah, the combusting the methane and oxygen is going to make it go. In fact, they have natural gas powered vehicles right now, but they don't have hot lead vehicles, do they? No. You know, a hot lead could work if you just build a little steam engine. You build a little steam engine there, hot chunk of iron, vaporizes the water, drives a turbine. And so the thing is, let's say I have a delta H here. Let's say the delta H is 3,000 kilojoules. My delta H. And then I could have a hot chunk of iron release 3,000 kilojoules. So a hot chunk of iron releasing 3,000 kilojoules of heat into my car, steam engine, versus burning this is going to make it drive the same distance because it's the same energy. No, the energy is quite a bit different. And so, you know, what we say is this, you know, heat is a much more random form of energy, much higher entropy form of energy than chemical potential energy. And therefore, you know, it's not as usable as this, because all this heat, what we call heat, delta H, you know, even though delta H is called the heat of reaction, delta H can be converted into heat and delta H, this is the first law of thermodynamics. You guys remember the first law of thermodynamics? Well, this is actually chapter 7 stuff. You didn't really review it. Delta H can be converted into heat and or work. Now, the thing about delta H is we can minimize the heat term to maximize the work. And so we could burn the methane and oxygen and do no work and have it all generate heat. Or we can burn it in an engine and do a lot of work and minimize the amount of heat, right? That's what we can do. And so this is a lot more useful than just having heat. If we just have heat, converting that into work isn't so easy. And so this is what I mean by energy entropy. And so in exothermic reactions, the entropy of the universe is increasing because the energy is going from a lower entropy form to a higher entropy form. Does it make sense? And so I came up with the initial driving forces in nature. The two driving forces in nature is to minimize energy. Minimizing energy does what? Minimizing energy actually increases the entropy of the universe. Because minimizing energy is a weird concept. It's a weird concept because do you know what the total energy content of the universe is? Because the weird thing is if the system's energy decreases, the surroundings energy must have increased. And so now you go, oh, decrease energy here, but increase energy there. Don't they self-cancel each other out? One is a driving force because we want to minimize energy. The other is increasing energy. We don't want that. And so the first law of thermodynamics states that the energy is conserved. That is, energy is neither created nor destroyed. And so if something's losing energy, then something else must be gaining that energy. And so how could that drive a reaction? Or can it? Right? Because the total energy content of the universe is constant. Right? The total energy content of the universe is fixed. And so what's driving reactions? What's driving reactions is the entropy. The entropy is not fixed. The second law of thermodynamics says for a spontaneous process to occur, the entropy of the universe must be increasing. So reactions are occurring right now, therefore the entropy of the universe must be continually increasing. When the entropy of the universe stops increasing is when we're dead, obviously, but nothing's going to happen. No reactions will occur. And so that is the second law of thermodynamics. And so when I say minimize energy, that's a little bit tricky because, yeah, we're minimizing energy for the system, but the surroundings is increasing energy, maximizing energy. And so, how do I reconcile those? Well, here's how I can reconcile those. And so this is the second law of thermodynamics. The second law of thermodynamics says we want to minimize energy and maximize entropy, because to minimize energy, this is going to come out negative. To maximize entropy, this term comes out positive, and the whole thing comes out negative. And so we have different scenarios here because we don't always maximize energy for the system. So let's talk about this. We're going to go back strictly to the system because that's what we care about. And so let's say the system is negative, the energy, and the entropy is positive. This is good. This is good. This is good. And so we say that this is spontaneous under all conditions. In other words, this is spontaneous at all temperatures. All temps. Because this is what we want. But let's say the energy is decreasing, but the entropy is also decreasing. So this is good, but this is bad. And so there's a question mark here. Versus if the energy is increasing for the system, that's bad. But if the entropy is also increasing, that's good. And so there's a question mark here. But if the energy is increasing and the entropy is decreasing, then this is bad and this is bad. And this is non-spontaneous under all conditions. In other words, at all temps. For reaction, good for reaction is what we mean. And so what about these two? Well, we have a conflict here. So which one dominates? Well, It depends. This one can be minimized. The entropy can be minimized by decreasing the temperature. And so for the first scenario here, we can say that this is spontaneous at low temperatures. Did I already do this? No. This is non-spontaneous at high temperatures. The second one here, oops. Yeah. The second one, what we want to do is we want to get the entropy to dominate. And so this would be spontaneous at high temperature, but non-spontaneous at low temperature. And so we'll look at these terms more again next time. So I'll stop here.